Hello and welcome. My name is Alan, and today we'll be doing more Ideas and Opinions by Albert Einstein. We will be doing two pieces of moderate length, so let's just go ahead and hop into this. The first piece I want to read is called Principles of Theoretical Physics. It's an inaugural address before the Prussian Academy of Sciences in 1914. Einstein became a member of the Prussian Academy in 1913. In 1933, after the advent of the Hitler regime, he resigned from the Academy, and this was published in Proceedings of the Prussian Academy of Sciences, 1914. Gentlemen, first of all, I have to thank you most heartily for conferring the greatest benefit on me that anybody can confer on a man like myself. By electing me to your academy, you have freed me from the distractions and cares of a professional life, so made it possible for me to devote myself entirely to scientific studies. I beg that you will continue to believe in my gratitude and my industry, even when my efforts seem to you to yield but a poor result. Perhaps I may be allowed apropos of this moment, a few general remarks on the relation of my sphere of activity, which is theoretical physics, toward elemental physics or experimental physics. A mathematician friend of mine said to me the other day, half in jest, the mathematician can do a lot of things, but never what you happen to want him to do just at the moment. Much the same often applies to the theoretical physicist when the experimental physicist calls him in. What is the reason for this peculiar lack of adaptability? The theorist's method involves he's using as a foundation general postulates or principles from which he can deduce conclusions. His work thus falls into two parts. He must first discover his principles and then draw the conclusion which follow from them. For the second of these tasks, he receives admirable equipment at school. If therefore the first of his problems has already been solved for some field or for a complex of related phenomena, he is certain of success, provided his industry and intelligence are adequate. The first of these tasks, namely that of establishing the principles which are to serve as the starting point of his deduction, is of an entirely different nature. Here there is no method capable of being learned and systematically applied so that it leads to the goal. The scientist has to worm these general principles out of nature by perceiving incomprehensive complexes of empirical facts, certain general features which permit of precise formulation. Once this formulation is successfully accomplished, inference follows on inference, often revealing unforeseen relations which extend far beyond the province of the reality from which the principles were drawn. But as long as no principles were found on which to base the deduction, the individual empirical fact is of no use to the theorist. Indeed, he cannot even do anything with isolated general laws abstracted from experience. He will remain helpless in the face of separate results of empirical research until principles which he can make the basis of deductive reasoning have revealed themselves to be. This is the kind of position in which theory finds itself at present in regard to the laws of heat radiation and molecular motion at low temperatures. About 15 years ago, nobody had yet doubted that a correct amount of electrical, optical, and thermal properties of matter was possible on the basis of Galileo Newtonian mechanics applied to molecular motion and on Maxwell's theory of the electromagnetic field. Then Planck showed that in order to establish a law of heat radiation constant with the experience, it was necessary to employ a method of calculation whose incompatibility with the principles of classical physics became clearer and clearer. For with this method of calculation, Planck introduced into physics the quantum hypothesis, which has since received brilliant confirmation. With this quantum hypothesis, he dethroned classical physics as applied to the case where sufficiently small masses move at sufficiently low speeds and sufficiently high rates of acceleration, so that today the laws of motion propounded by Galileo and Newton can only be accepted as limiting laws. In spite of assiduous efforts, however, the theorists have not yet succeeded in replacing the principles of mechanics by others which fit in with Planck's laws of heat radiation or the quantum hypothesis. No matter how definitely it has been established that heat is to be explained by molecular motion, we have nevertheless to admit today that our position in regard to the fundamental laws of this motion resembles that of the astronomers before Newton in regard to the motions of the planets. I have just now referred to a group of facts for the theoretical treatment of which the principles are lacking, but it may equally well happen that clearly formulated principles lead to the conclusions which fall entirely or almost entirely outside of the sphere of reality at present accessible to our experience. In that case, it may need many years of empirical research to ascertain whether the theoretical principles correspond with reality. We have an instance of this in the theory of relativity. An analysis of the fundamental concepts of space and time has shown that the principle of the constant velocity of light is shown in empty space, which emerges from the optics of the bodies in motion, by no means forces us to accept the theory of a stationary luminiferous ether. On the contrary, it has been possible to frame a general theory which takes account of the fact that experiments carried out on the Earth never reveal any transitory motion of the Earth. This involves using the principle of relativity, which says that the laws of nature do not alter their form when one passes from the original admissible system of coordinates to a new one, which is in uniform translatory motion with respect to it. This theory has received substantial confirmation from experience and has led to a simplification of the theoretical description of groups of facts already connected. On the other hand, from the theoretical point of view, this theory is not wholly satisfactory because of the principle of relativity just formulated favors uniform motion. If it is true that no absolute significance must be attached to uniform motion from the physical point of view, the question arises whether this statement must not also be extended to the non-uniform motions. It has turned out that one arrives at an unambiguous extension of the relativity theory if one postulates a principle of relativity in this extended sense. One is led thereby to a general theory of gravitation which includes dynamics. For the present, however, we have not the necessary array of facts to test the legitimacy of our introduction of the postulated principle. We have ascertained that inductive physics asks questions of deductive and vice versa, the answers to which demand the exertion of all our energies. May we soon succeed in making permanent progress by our united efforts. So yeah, Einstein doing a lot of talk on the theory of relativity as well as a number of other laws, following upon his acceptance into the Prussian Academy of Sciences. The other piece we're going to read is called Principles of Research, and it is an address delivered at a celebration of Max Planck's 60th birthday, 1918, before the Physical Society in Berlin, published in Mein Weltbild, Amsterdam, Corrido Verlag, 1934. Max Planck, 1858 to 1947, was for many years professor of theoretical physics at the University of Berlin. By far the most outstanding of his contributions to physics is his quantum theory, which he advanced in 1900 and which has provided the basis for the whole development of modern atomic physics. Next to Planck, it was Einstein who did the pioneering work in the young field, above all in his theory of quanta or photons, 1905, and his theory of specific heats, 1907. It was he who perceived more than anyone else the fundamental and pervasive character of the quantum concept in all its ramifications. In the temple of science are many mansions, and various indeed are they that dwell therein, and the motives that have led them hither. Many take the science out of the joyful sense of superior intellectual power. Science is their own special sport to which they look for vivid experience and the satisfaction of ambition. Many others are to be found in the temple who have offered the products of their brains on this altar for purely utilitarian purposes. Were an angel of the Lord to come and drive all the people belonging to these two categories out of the temple, the assemblage would be seriously depleted, but there would still be some men of both present and past times left inside. Our Planck is one of them, and that is why we love him. I am quite aware that we have just now light-heartedly expelled in imagination many excellent men who are largely, perhaps chiefly, responsible for the building of the temple of science, and in many cases our angel would find it a pretty ticklish job to decide. But the one thing I feel sure, if the types we have expelled were the only types there were, the temple would never have come to be, any more than the forest can grow, which consists of nothing but creepers. For these people, any sphere of human activity will do if it comes to a point. Whether they have become engineers, officers, tradesmen, or scientists depends on circumstances. Now let us have another look at those who have found favor with the angel. Most of them are somewhat odd, uncommunicative, solitary fellows, really less like each other, in spite of these common characteristics, than the hosts of the rejected. What has brought them to the temple? That is a difficult question, and no single answer will cover it. To begin with, I believe that that one of the strongest motives that leads men to art and science is escape from everyday life and its painful crudity and hopeless dreariness from the fetters of one's own ever-shifting desires. A finely tempered nature longs to escape from personal life into the world of objective perception and thought. This desire may be compared with the townsman's irresponsible longing to escape from this noisy, cramped surrounding into the silence of high mountains where the eyes range freely through the still, pure air and fondly traces out the restful contours apparently built for eternity. With this negative motive, there goes a positive one. Man tries to make for himself in the fashion that suits him best a simplified and intelligible picture of the world. He then tries to some extent to substitute this cosmos for the world of experience, and thus to overcome it. This is what the painter, the poet, and the relative and the speculative philosopher and the natural scientist do, each in his own fashion. Each makes this cosmos and his construction the pivot of his emotional life in order to find in this way the peace and security which he cannot find in the narrow whirlpool of personal experience. What place does the theoretical physicist picture of the world occupy among all these possible pictures? It demands the highest possible standards of rigorous perception or precision in the description of relations, such as only in the use of mathematical language can give. In regard to his subject matter, on the other hand, the physicist has to limit himself very severely. He must content himself with describing the simple events which can be brought within the domain of our experience. All events of a more complex order are beyond the power of the human intellect to reconstruct with the subtle accuracy and logical perfection which the theoretical physicist demands. Supreme purity, clarity, and certainty at the cost of completeness. But what can the attraction of getting to know such a tiny section of nature thoroughly while one leaves everything subtler and more complex shyly and timidly alone? Does the product of such a modest effort deserve to be called by the proud name of a theory of the universe? In my belief, the name is justified. For the general laws on which the structure of theoretical physics is based claim to be valid for any natural phenomenon whatsoever. With them, it ought to be possible to arrive at the description, that is to say, the theory of every natural process, including life, by means of pure deduction. If the process of deduction were not for beyond the capacity of the human intellect, the physicist's renunciation of completeness for his cosmos is therefore not a matter of fundamental principle. The supreme task of the physicist is to arrive at those universal elementary laws from which the cosmos can be built up by pure deduction. There is no logical path to these laws, only intuition, resting on sympathetic understanding of experience, can reach them. In this methodological uncertainty, one might oppose that there were any number of possible systems of theoretical physics, all equally well justified. And this opinion is no doubt correct, theoretically. But the development of physics has shown that at any given moment, out of all conceivable constructions, a single one has always proved itself decidedly superior to all of the rest. Nobody who has really gone deeply into the matter will deny that in practice, the world of phenomena uniquely determines the theoretical system, in spite of the fact that there is no logical bridge between phenomena and their theoretical principles. This is what Leibniz described so happily as a pre-established harmony. Physicists often accuse epistemologists of not paying sufficient attention to this act or fact. Here it seems to me lie the roots of the controversy carried on some years ago between Mach and Planck. The longing to behold this pre-established harmony in the source is the source of the inexhaustible patience and the perseverance with which Planck has devoted himself, as we see, to the most general problems of our science, refusing to let himself be diverted to more grateful and more easily attained ends. I have often heard colleagues try to attribute this attitude of his to extraordinary willpower and discipline wrongly. In my opinion, the state of mind which enables a man to do work of this kind is akin to that of the religious worshipper or the lover. The daily effort comes from no deliberate intention or program, but straight from the heart. There he sits, our beloved Planck, and smiles inside himself at my childish playing about with the lantern of Diogenes. Our affection for him needs no threadbare explanation. May the love of science continue to illuminate the path in the future and lead him to the solution of the most important problem in present day physics, which he has himself posed and done so much to solve. May he succeed in uniting quantum theory and electrodynamics and mechanics in a single logical system. So, yeah, Einstein painting his reverence for physicist Max Planck, who is also a big name in uh, physics, if you did not know. So, Einstein is not the end all be all of science. There's a lot more out there. Max Planck's one of the bigger names as well. So, but that will be all for this episode. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.